to start. So subspace of a vector space, discussed linear span. We showed that linear span of a subset of a vector space is a subspace and is the smallest subspace of V which contains a given subset. I introduced 4 fundamental subspaces associated to a matrix. Remember these 4 fundamental subspaces. These are very important. We will meet them all the time. So the row space of a M by N matrix over a field of scalars, and take a M by N matrix and look at the rows of the matrix. Yeah. The rows are living in today's real matrix. They live inside n-dimensional Euclidean. So we have row vectors. So this is a subset of Fn, and look at the linear. So take the linear span of all the row vectors of a matrix. That is called the row space. Then we can consider the null space of a matrix. The null space is simply the set of all solutions of the homogeneous system of equations x equal to 0. So given homogeneous system of linear x equal to null space of the given matrix. So we know all system of linear equations. We apply row operations, convert A into row echelon form or row canonical form, do the back substitution, and you will find all the solutions. Just a minute. Okay. So yes, yeah, Prakhar, you have a question? Okay. So the row space and the null space. So they are living inside the n-dimensional space Fn. I'll introduce dimensional vectors just using this word. Fn is called the n-dimensional vector space over Fn, and look at all the solutions of Ax equal to 0. That is called the null space. So these are the vectors which are in a way killed by the action. And then the row space is simply, we have proved before that if I take solutions of Ax equal to 0 and take linear combinations of finitely many solutions of Ax equal to 0, that is also a solution of Ax. So null space of a matrix is a subspace of Fn. The row space of a matrix, which is linear span of the row vectors of A, that is also a subspace of I. Now, if you have M by N matrix, we have 2 vector spaces associated with this, namely the Fm, Fm and F. Fn has 2 subspaces, null space and row space. Okay. Now we look at the column space. The column space. How many columns are there? There are in a given M by N matrix. There are n columns, and we can each and every column is living inside the m-dimensional space Fm. Every column lives inside Fm, and I have n columns. Look at the linear span of all the column vectors. That is called the column space of the given matrix. Yeah, but we know that if I take the transpose of the matrix, and the rows of the transpose are exactly columns of the matrix A. Okay, so column space is also, it's like a row space, but then we take the row space of A transpose. Yeah. So corresponding to row space, I have column space, but the column space is the row space of A transpose, and corresponding to null space, I can also consider null space of A transpose. Just as I looked at column space, which was the row space of A transpose, I can also look at the null space of A transpose. Yeah? So null space of A transpose is simply all x, so that x times A is 0. Yeah? X times A equal to 0. That is same as null space. So x times A equal to, this means if I take the transpose, then this is same as this equal to 0. Okay, XA is a row. Yeah, XA is a row vector, and its transpose is a column vector. XA transpose is a column vector, but that is same as A transpose times X transpose. Yeah. So therefore, X transpose belongs to null space of A transpose. Okay. So we look at the null space of A is all solutions of AX equal to 0. This is the null space. And all solutions of A transpose X equal to 0, this is the null space of A transpose, right? So this is same as saying that X transpose A equal to 0, and the set of all such row vectors as a set of all such row vectors. Okay? So these are in FM. Okay? And X transpose A equal to XA equal to 0. So this is the null space of A transpose. So corresponding to a given matrix A, I can look at two systems of linear equations, homogeneous system of linear equations, AX equal to 0 or A transpose X. So AX equal to 0 is the set of all X which satisfy AX the null space, and set of all X which satisfy XA equal to 0 is simply the null space of A transpose. So I have two null spaces, and I have two row spaces, the row space of A and the row space of A transpose. Row space of A transpose is same as the column space. So these subspaces are associated with a given M by N matrix. Okay, we will meet these four subspaces later. Yeah, lot of linear algebra is concerning identifying, computing these four subspaces of a given matrix. Yeah. Okay. So let us proceed. Yeah. Linear span of a set. So different sets, they span the same subspace. Yeah. For example, if I look at the standard column vectors E1 and E2, standard column vectors E1 and E2, E1 and E2 in a two-dimensional space. E1 and E2, they live inside R2. So here is E1 and here is E2. And if I take the linear span of E1 and E2, that is the whole space R2. Yeah, that is the whole space R2. Because every element of R2, it looks like XY, and XY can be written as XE1 plus YE2. So this belongs to linear span of E1 and E2. But you can check very easily that linear span of E1 and E1 plus E2, that is also R2. Yeah? So if I take any linear span of E1 and E1 plus E2, that is same as A1 plus A2 E1 plus A2 E2. So any linear combination of E1 and E2 I can write in this form, and vice versa. So these two subsets E1 and E1 plus E2, or E1 and E2, their linear span is the same space R2. So a given vector space can be linear span of many sets of vectors. Yeah, many sets of vectors, and we need to understand what are the common properties of subsets whose linear span is a given vector space. Okay, look at the vector space of P and R. So P and R is the vector space of all polynomials T. So P and R are polynomials, general polynomials like A0 plus A1t plus A2t square plus ANTN, and you can check this is also spanned by 1 t minus a to the n. For any, you fix a real number and take Taylor. You have studied Taylor expansion of a function which has derivatives up to order n. I can take Taylor expansion and write the given function in terms of powers of x minus a. So given polynomial of degree n at most, I can write Taylor expansion around t, and then the coefficients will be derivatives of the given polynomial at t equal to. So every polynomial of degree at most n can be written as a linear combination of these polynomials 1, t minus a to the power n, and so this is a linear span. The linear span of these n plus 1 polynomials is same as linear span of these n polynomials. Yeah. So if I change this a, keep on changing a, I will see that P and R is linear span of infinitely many kinds of subsets of P and R. Yeah. Okay. Yeah. So the question is, which spaces can be spanned by finitely many elements? So P and R is linear span of n plus 1 polynomial. R2 is linear span of 2 vectors, E1, E2, or E1 plus E2. Yeah. So the question arises, what are the subspace, what are the vector spaces which can be linear span of finitely many elements in that space? Okay. So if V is linear span of a subset of and suppose it is a finite set, then how many elements smallest such set have? Okay. We, for sake of economy, we would like to realize a given vector space as linear span of small in R2. R2 was linear span of E1 and E2. Now, geometrically, you can believe that R2 cannot be linear span of one vector, because if I take one vector in R2, what is its linear span? It will be multiples of scalar multiples of this vector, but they will all lie on this line which contains this. Linear span of one non-zero vector in R2, it is the entire line passing through origin which contains that vector. Okay, yeah. So if I took E1 plus E2, it looks like this. This is the line passing through. All the points on this line represent vectors which are linear span of one single vector, E1 plus E2. If I take, say, E2, then its linear span is the entire y-axis. Okay. If I take E1, its linear span is the entire x-axis. So I cannot get R2 as linear span of a single non-zero vector. Right? I need at least two vectors, and we will see that it is enough. Okay, we can realize R2 as a linear span of two vectors, and you don't need more than two vectors. Okay, yeah. So, but then it's not clear. It's not clear at this point whether any two subsets S will have same number of elements if those subsets have the property that no proper subset of S can give rise to a subspace, the whole space. Okay, so we want to address this question, and in order to do that, we need the notion of very important notions of linear dependence and linear independence, basis and dimension. Okay, these are four very important words: linear independence, basis, and dimension of a vector space. And once we understand this, we will be able to prove that if a vector space is finite dimensional, that is, it is linear span of V, then any two smallest subsets whose linear span is the whole space will have same number of elements, and that number will be called dimension. So let us justify these words, that dimension is a unique number associated with a vector space. So it will turn out that R2 is two-dimensional. It is linear span of two vectors, and it can't be obtained as linear span of one. Then P and R, okay, it is linear span of these n plus 1 polynomials. Okay. It cannot be linear span of less than n plus 1 polynomial. We'll see that. Okay. So P and R will have dimension n plus, and R2 will have dimension n. similarly, if I take Rn, it is linear span of n standard basic column vectors E1, En. So Rn will have so whatever concept of dimension we want to accept, it should coincide with our geometric intuition that the Cartesian plane should be two-dimensional. There are 2 degrees of freedom in Cartesian plane. Yeah, every point can be represented by 2 coordinates. Similarly, if I take real line, it should be a one-dimensional space because it has 1 degree of freedom. Basically, it has 1 degree of freedom. Okay? Then in R3, there are 3 degrees of freedom. Every point is uniquely represented by 3 coordinates, and Rn has n dimension. So we want to make this notion precise. What is the dimension of a vector space? Okay. So suppose V is a vector space. Okay? Suppose V is a vector space. Then a subset of V is called linearly dependent. Okay? A subset of V is called linearly dependent if there exist distinct vectors. Yeah, if there exist distinct vectors, the distinct is important. V1, V2, Vn, there are n distinct vectors and scalars alpha 1, alpha 2, alpha n, so that these are not all zero. Okay, I have these n scalars which are not all zero. At least one of them is non-zero, and I have n distinct vectors such that this linear combination alpha 1 v1 alpha 2 v2 alpha n vn is 0. Okay, then we say these distinct vectors v1 v2 vn are linearly dependent. Okay, so linear dependence means I have a linear equation where the coefficients are the scalars, and this linear combination produces the zero vector, and it's a non-trivial linear combination. Yeah. So suppose I just take a non-zero vector, one non-zero vector. Yeah. Then it cannot be linearly dependent, because if a scalar times a non-zero vector is 0, that scalar be equal to 0. You can use the axioms of vector space. Yeah. These are axioms of a arbitrary vector space, and show that if non-zero vector times a scalar is 0, that scalar must be 0.